All right. Good evening, everyone. I hope you're all doing fine. There's a little bit background noise over here. Apologies if I'm a little bit unclear. But let me quickly introduce myself. My name is Lakmal Warusawithana, and I'll be your host for today. So, what exactly is today? Today is a day where we'll be joined by a very special speaker who is from WSO2, and he's a senior director of solutions architecture over there. And what we'll be doing today is he'll be speaking to us on how we can actually use Kubernetes and eBPF. I have no idea what that is, but hopefully by the end of this session, I will be doing so. But before I quickly hand over the stream to Mr. Lakmal Warusawithana, let me give you a quick heads up. There's a small announcement coming towards the end, and I think that quite many of you might like it. And until then, stay tuned. So, Lakmal, the stream is yours.
Thanks, Akalanka. Good afternoon and good evening who is joining in Australia, and I don't know, good morning who is joining in US. So this is a virtual event, so I don't know where you guys are joining. Yeah, and I'm sorry, so I have some kind of cough and a cold, so my voice is might be not clear, so I will try my best. Okay. Can you see my screen? You can see it, right? Okay. Yeah. Before we dive into deep technical details, let's briefly find out what's the traditional data plane and what's the programmable data plane. Traditional data plane refers to specialized hardware configurations such as like routers and switches, and typically they are managed directly via their respective consoles. To modify these configurations, so we have to manually access these consoles and take the necessary changes. And on the other hand, programmable data plane provide a dynamic control and manipulation network behavior. So instead of relying on manual adjustment to specific hardware devices, programmable data plane allows for network configuration and the changes to be made to a software. And so that has a greater flexibility, scalability, and adaptability to evolving the demand of cloud native applications. So let's find out more details. And important thing is in such network manipulation software can commodity run on commodity hardware, and that eliminates the needs of special equipment. Can you see my screen? The sites are moving.
The slides are not moving actually, Lakmal.
Okay, let me try it. Okay, now it's working, right?
Yeah, all good.
Okay, sorry about that. Yeah, so let's move on. So we discussed that so we can control intercommunication via these software platforms, right? So for example, such network manipulation software like software defined network, we call it SDN, and network function virtualization, we call it NFV, and extended Berkeley packet filter, that's eBPF. So today we are more find out more detail on eBPF. So you can so let's see how we can program a data plane with this software. This is where concept of control plane and data planes comes into play. So different network policies can be defined in the control plane, and these policies can be enforced into the data plane. This loosely coupled architecture allows a single control plane to manage multiple data planes, and it provides greater scalability and flexibility. Okay, so let's explore the role of the Kubernetes and Service Mesh platform play in this context. So both Kubernetes and Service Mesh platform provide a higher level of network abstraction, like including deployments, pods, services, ingress, egress, and more, right? Additionally, we can manage this network behavior in data plane using this abstraction. So which are controlled by the policies that we define in the control plane. By combining these high-level abstraction with like a technologies like eBPF, we can create a highly powerful data plane. This programmable data plane can be easily tailored to meet to evolving needs of cloud native application. Okay, so let's find out more detail of eBPF. eBPF, extended Berkeley packet filter, it's a technology that allows developers to run custom program in the Linux kernel and without needing to change the kernel source and without loading a custom kernel module. In another word, like it provides a way to safely and efficiently extend the capabilities of the Linux kernel to custom use. And also you may also think about what is this weird name is. So BPF originally stood for Berkeley packet filter, but now that eBPF, extended BPF, can do so much more than the packet filtering, but the acronym is no longer makes sense. So eBPF is now considered a standalone term that doesn't stand for anything. So why has this eBPF become so popular, and what impact has it had in the Linux kernel ecosystem? As we all know that more than 90% of cloud infrastructures is running top of Linux because Linux is more robust, stable, and reliable. This diagram illustrates Linux kernel architecture. So the Linux kernel provide a higher level of abstractions, allowing for application to run and share the resources. On the other hand, and as application architecture are rapidly evolving, if we require additional kernel level functionality, traditionally we had only two options. Option one is native support, where you change kernel source code and convince the Linux kernel community to incorporate the changes. But for this, we might wait for several years for new kernel version to be incorporate your changes and to be available in default kernel release. And the second option is write a kernel module. But the risk of but it has a risk and the complexity because we might need to fix it up regularly, as every kernel release may break it. So these were some of the major challenges we faced during the evaluation of modern cloud native application. With eBPF, the new option is available. So that allows for reprogramming the behavior of the Linux kernel without requiring changes to the source code, kernel source code, or loading kernel module. Okay, so let's find out how eBPF work. eBPF program can attach to different types of low-level hooks in the kernel. And these hooks are like triggered by certain kernel or user space events, such as like system calls, network events, or some trace point. For example, eBPF can hook into a system call like read write made by the user space program, right? At the network level, it can inspect or modify network packets and implement some custom routing or firewall rules or gather some network statistics. And eBPF can also inspect file system operation, like such as open, read, or write calls on a file. And this can be used to monitor file access, implement some access control, or gather some I/O metrics. Is eBPF safe? What do you think? Yes, eBPF is designed to be safe to use in production environment. Here are few reasons why. First one is the verification. So before an eBPF program is loaded into the kernel, it goes through a verification process. This process checks for things like infinite loops and out of bound memory access and some unsafe operations. Only if the program passes this strict verification process, it is loaded and executed. And the second one is isolation. So eBPF program are executed in a dedicated virtual machine within the kernel. So it's isolated from the rest of the system. And this helps prevent any adverse effect from spreading to the rest of the system. Also, the just-in compiler. So just-in compiler is a critical part of the eBPF architecture in the kernel. When an eBPF program is loaded into the kernel, it's initially in an architectural neutral intermediate representation. So this is what checked by the verifier for safety. Once the program has passed the verification, so it could be interpreted directly, but interpretation has significant overhead. To improve performance, the Linux kernel can translate these eBPF program to native machine code for the host CPU. And this translation process is done by eBPF Git compiler. The result is a set of instructions that can be executed directly by the CPU. Okay, let's find out how we can develop eBPF program. You can use many different tools to develop eBPF program, such as BCC, BPF trace, and libbpf. There are so many other tools also, and each of these tools comes with its own strength and weakness. So the choice of this tool depends on the special use case and the programming language you are most comfortable with. So BCC includes a set of pre-built tools that use eBPF to provide detailed insight into like system behavior, such as latency analysis, network packet capturing, and more. So this image shows a very few tools that you can find out under BCC, and these tools trigger different events in kernel space and as well as the user space. Okay, let's move on. So So we have now rough idea what's eBPF and how it's work. So let's find out the eBPF impact on cloud native ecosystem. So I know you all already know of, how Kubernetes is working. So so in this Kubernetes, service is an abstraction layer that provide a stable IP address for a set of ports, right? And when a Kubernetes service is created, it is assigned a virtual IP address, also known as a cluster IP, and a port number. So this IP address is virtual in the sense that it does not correspond to a physical network interface on any node in the cluster. Instead, it uses as a stable endpoint for service, even as individual ports come and go. So when a client send a traffic to the service IP address and the port, this traffic is intercepted by a network proxy called kube-proxy, which run on every node in the cluster. The kube-proxy maintain a set of rules in the local IP tables on each node that redirect traffic from the service's virtual IP address to one of the port associated in the service. So this translation need to be happen each and every packet. To be more precise, so when a request with a payload is sent, the payload is divided into one or more packets at the transport layer in the TCP, and each packet is then encapsulated with an IP packet at the network layer. The IP header of this packet is then translate using NAT, which involves changing the source and no destination IP address in the header. Because NAT is applied each IP packet individually, the translation need to be done for each and every packet that is sent or received. This can introduce additional overhead and latency in the network, especially in the case where a large number of packets need to be translated. So in order to address these performance and scalability issues, the iptable based kube-proxy and Cilium is an open source software product in CCM project. So Cilium provide an alternative socket-based load balancing mode of operations. So in socket-based load balancing mode, Cilium create a listener socket and bind it to the determining the appropriate service endpoint where to route, and it uses the eBPFs to redirect the packet to the endpoint socket. So this translation happen once per connection, not per each packet. And this gives a network level performance boost. So this diagram shows some performance comparison between iptable based kube-proxy and eBPF socket based load balancing. So if you look at this graph, so eBPF socket based load balancing has better performance than iptable based kube-proxy. So in summary, use of eBPF allows for more efficient and fine-grained packet processing in the kernel, which can reduce latency and increase throughput. Okay. So the one other important thing is the network security, right? The network security is very important because it's helped to protect the communication and the data flowing over the network from unauthorized access, interception, and modification. So the IP-based network security relies on controlling access based on the IP address, which are assigned to device on the network. For example, a firewall might allow or block access to a particular IP addresses or IP address or range of IP addresses, right? However, the IP-based security has limitation. So as the IP address can be easily spoofed, right? Or it can be manipulated and making it difficult to determine the true identity of the user or application. So, and this is especially problematic in like Kubernetes environment, where applications are highly dynamic and in parallel with IP addresses that are constantly changing. So eBPF identity-based policies can control egress calls from port by leveraging the rich set of metadata that's available in the eBPF maps. The metadata include information such as labels and annotations, and this information can be used to enforce security policies based on the identity. So this metadata can be used to match against policies that define who is allowed to access which services, and the policies can be enforced by using eBPF program loaded into the kernel. For example, when a packet is sent from a port, an eBPF program can extract the port metadata from the packet and check if the port is allowed to access the service, and then either permit or drop the packet accordingly. This provides a highly granular way to control access to service based on the identity rather than relying on the IP address. In addition to controlling the egress, eBPF can also enforce policies for ingress traffic at the destination port. When a packet is received by a pod, an eBPF program can extract the metadata from the packet and use it to enforce security policies. For example, the program can check if the packet is coming from an unauthorized sources and it is not carrying any malicious payload, and then either it's allowed or block the packet accordingly. Okay, so next section I want to talk about the observability. So what is observability? The observability is the practice of like gaining insight into a behavior of a system through various type of data, so such as metrics, logs, and traces. So current observability practice often rely on manual instrumentation, which involves adding code to a specific area of the system to collect and analyze data. And this process can be complex and also time consuming, and it may create a barrier to entry for organizations that looking to implement observability in their environment. And on the other hand, the service mesh sidecar proxies is a very popular approach for providing observability in microservice environment. So sidecar proxies can like automatically instrument the request response traffic and generate telemetry data, which can be collected and then analyzed by the service mesh control plane to provide visibility into the application behavior. But however, in this approach comes with the overhead of running separate sidecar proxy for each service interface, which can impact performance and resource utilization. So eBPF provide an alternative approach to observability in a service mesh environment by allowing kernel level instrumentation. So this means that telemetry data can be collected without the need for a separate sidecar proxy, reducing overhead and resource utilization. So eBPF program can used to capture network traffic and inspect and modify the packets and generate telemetry data for analysis by a centralized observability platform. And this allows for deep visibility into the application behavior and the underlying infrastructure without overhead of sidecar proxy. So two open source projects like Pixie and the Hubble leverage this eBPF technology to provide deeper observability in cloud native environment. So I will show some of the capabilities of these tools in a few minutes while I do a demo. This is a Pixie graph. The Pixie eBPF is based on this flamegraph can help to identify performance issues within the application code by like providing a visual representation of where the time is being spent during the execution. That this frame graph can be identified like a bottlenecks in the application code, such as the function or the method that are taking up significant amount of time, and can help developers to optimize their code to improve performance. And the beauty is this frame graph is generated without changing application code. Okay, so let's move into the demo. Let me try to can you see my screen? So I want to have a presentation and my console side by side.
Yeah, it's great.
Can you see the
Seeing two screens, I see the console and the slides as well.
and can you read the
It's a little bit
commands?
difficult to
Difficult.
read.
Okay, let me try to
Yes.
increase. Can
Okay.
now?
Yeah, possible.
Okay, cool.
A little bit.
Okay, so let me. So the first demo I want to do to demonstrate the the identity identity based network security. So basically, we discussed what's the limitation in the IP based network security. So here, I want to demonstrate how CDM use identity based network security. So to demonstrate, this is a Cilium project sample. So demonstrate this scenario. So I'm using their own sample demo. Basically, to demonstrate, so this setup has running different ports. So I have a one port called TIE Fighter. It's at a label called Oak Empire and the class TIE Fighter, and there's another port running label has Oak Alliance and class X-Wing, and then the other port is running two deployment running two ports. It's Oak Empire and class Death Star, right? So basically, I'm not sure if you are familiar with the Star Wars, you can identify these names, right? So basically, let me get okay. I want to get the Examples, not this one. We're going to get some commands. I don't want to memorize it. Okay. Right. Okay. Hope you can see. So let me get. So I have my the setup is running. So you can see 2 ports running with the DEXA and the 1 port running TIE Fighter and 1 port for X-Wing. And I have the service called DEXA and the so let me first basically I'm running a I am running a command exec command in the X-Wing. In this case, I am calling DEXA endpoint to get a landing permission. So basically what I'm doing is I'm running exec curl command inside the X-Wing and calling the DEXA endpoint, right? So if I run this, it should say ship landed. Just give the permission. This is like a demonstration, right? It's allowed the landing permission. The ship is landed now. So I can do the same thing to the from the basically TIE Fighter. So if I run the same command, you can see it's allow the permission and ship is landed. So I can call the DEXA endpoint from either in the TIE Fighter ports or either in the X-Wing port. So there's no policy as enforced in this case. So let's find out the policy. First, I will enforce a layer 3 policy. So this is a Cilium network policy. So if you look at this policy, so here, so this policy is applying to this endpoint called endpoint is select by using labels. So Oak, Empire, and class DEXA, right? So basically, this policy is enforced into this endpoint via the endpoint selector. And what are the policy? The English policy saying that from endpoints. So if the from endpoints matches like the Oak Empire, this Oak Empire, right? Oak Empire, it's Oak Empire. Oak Empire. So I am allowing to call this backend. This the DEXA endpoint. So here, so I'm using the port identity or the application identity, right? The labels. So I'm not using any IP level informations. So I'm defining my policy using the labels that is identity, right? So let's apply this and see. Let me apply this. So it is applied now. Now see, so with this policy, what we can expect is, let me try to go to the, this is the behavior we are expecting. Basically, we want only to allow if the label carried Oak Empire to communicate with this endpoint. If other than that Oak Empire shouldn't allow to carry the communication. So this layer 3 enforcement. So basically, if someone trying to call without having the proper label, that packet will be dropped. So that's the expected behavior we are looking at. Now let me run the TIE Fighter command. So basically, so I am trying to use the same command we ran earlier. So from the TIE Fighter, it should run, right? So I say chip landed. So I can call that endpoint. Basically, it's allowed to call the endpoint. And now let me try to run from the X-Wing. So I'm running from the Xwin, right? Now you can see you are not getting in response because this is enforcing in the layer 3. The network packet is dropped now. So it will time out, and eventually you can't call this endpoint because we put a policy saying that with the identity information only you can communicate the Death Star which only carry the label called or Empire. So in this case, the Xwin doesn't have the Empire label, so the network level is packet is dropped now. Okay. Then the next thing what I want to show is the layer 7 enforcement. So in that case, let me try to use that. So this is the behavior we are going to check the next step. Basically, there's the endpoint in the Empire, the Death Star. There's this is like a demo endpoint. So basically, if you call this endpoint, it will exploit the port, basically exhaust the star port. Let me try and show you. So basically, this is a sample. So basically, if that call the Death Star is explored, right? Now, say if you identify some issue in your resource endpoint, now you want to block this. So this blocking should be happening to the layer 7 now. It's application layer. So basically, let's see how we can protect this. So let me show you another policy, the layer 7 policy. So this same as the above policy. So we have the endpoint selector. This is applying to the Death Star, and in this we are only allowing Empire or Empire labels, and to port we are allowing by defining by allowing the HTTP port, and the rule saying that only allowing request landing method. So only other than this one is different endpoint resource path. So by putting this policy, you can limit your exposing resource path other than what to define in this policy. So let me apply this. So it's applied now. Now if I try to call this endpoint, the resource end path, it called access in it is enforced in the layer 7. So they are running in Cilium case, they are running on proxy node level, not in the sidecar. As a sidecar, it's running a per node, not node proxy, and enforcing this policy. And because of layer 7, we can say this access is denied. It's not a layer 3, but just not a packet dropping. It's basically send the response saying that you can't access this particular resource. So you can see, there are many things you can do with this identity-based policy enforcement. So these things can do because we can manipulate the network behavior by using eBPF, by adding the identity of the pod identity into the network communication. So it's happening automatically without doing any changes in the application code. So these things can very useful if you are maintaining a larger cluster, and also you can build top of different application features using this kind of technology. So this is where the eBPF change in the cloud native ecosystem, because like I said earlier, if you want to do this kind of thing, we need to change the Linux source code, or either we had to develop our own kernel module. But with the eBPF, without changing the Linux code source code, we can run eBPF program and do this kind of thing. And next thing I want to show is basically, so I am running. So this is I couldn't show you. So this I have two laptops here. I am running two clusters. So this one I am running So I'm installed Cilium in my laptop, and so I'm running Cilium with Hubble also enabled. So in Hubble, I'm running Hubble is the observability layer built on top of Cilium. So I am use Hubble in relay mode here. So I'm uh, like collecting the data from eBPF, and in this scenario, I am representing this collected data in using Grafana Prometheus, the observability clusters. So you can see this is generating from this setup. All the request count, the HTTP status, latency, these things can be captured by using eBPF interception, and you can find out deeper insight of what happening in your cluster or application without doing any manual instrumentation by using this eBPF technology. So I just want to show these things can be collected from the eBPF player. So there are some tracing point also you can capture. You can capture the different if you have in the tracing ID in your packet, you can capture the different tracing capabilities. Then the third thing I want to show you, so here, so I have installed Pixie in my other laptop. So let me see, I think it's went to sleep. Let me try to wake it up. Give me a couple of, so I am running. So this is, I have access to my other laptop. See. Yeah, so I am running Pixie. So I have installed Pixie in that. So Pixie has some daemon sets running in the Kubernetes cluster. Then it intercept the eBPF programs, the different tracing point, and collect the data. And in this case, it use the Pixie cloud, community cloud, to summarize and represent the collected data in this cluster. So let me try to get this work. Okay. Yeah, I think it takes up a couple of minutes. Second to boot it up. Okay, it's getting okay now. Right. So you can see this is a service graph. So this graph is created dynamically based on the network activity that happening in the cluster. Depending on the, so I am running a this load test environment in this particular namespace, and so it will do different calls to different endpoints in this application. So it will create this network communication, right? Then based on that communication, you can create this service graph dynamically. And also, if you go mouse over to this particular line, the line represent the actual communication happen with this port to this port, basically. And of course, you can see the what's are the percentile 50 latency, percentile 99% latency. So likewise, and there are any error rate. So if you go to this one, you can see there's error rate. Likewise, you can identify the high level view by looking at the service graph, and you can go into the detail by just clicking some of these details. So basically, now we are in the it's we are looking at a particular port level metrics. You can correlate these things at when the HTTP request happen. There's an error in the other console, you can see, and there's latency when that happens. So like this, all this information is captured without manual instrumentation. It's captured through the eBPF programs. And if you go to the let me see. So you can see now it's growing this service graph, right? So it call in different endpoints based on the network activity. It will grow basically. It will, And also you can identify any abnormal connection to the outside of the cluster, because it also capture that. And these things you very important to like debug is there any abnormal activity in your particular in the operation point of view. And let me try to get the HTTP data. So this also can capture the different HTTP data packets also. Some cases you can see the packet data, its payload itself also. For example, you can see it can capture the packet also. And let me find out any error scenario. And HTTP header, everything is captured, and it is nicely summarized, give the very nice UI also. Okay, so this is a two open source project, Cilium and Pixie. Pixie is mainly focusing on the observability layer. Then the Cilium is playing on the network security and the network the optimization, as well as the Cilium project has this project called Hubble that's focusing on the observability layer. So I think this is what I want to show you. So I have put the references in my slide deck. So I have written an article based on the what I did today as a talk. And also, if you are interested in understanding eBPF, I highly recommend to go to the eBPF.io. It's very nice. The many of the diagram today I showed you are taken from that particular website. That's very nice way of explaining the things. And also Cilium and Pixie are the two mainstream projects that leverage in this eBPF, and there are a few other projects also. For example, we can use eBPF for the runtime security. So basically, if there are any abnormalities happening in the runtime, we can alert it. Like the Cilium has a project called Tetron, something like that. So that gives the runtime security. And there's another project called Falco. So Falco also able to alert any alert based on any malicious activity happening in the runtime. So all these things are created by using eBPF technology. Yeah, so I think this is what I want to share with you. So basically, if I can take any question, if I have the time, we have 10 minutes, right? Yeah.
All right, just give them some time. If you have any questions, just feel free to drop something in the chat. I believe we don't have any. So in that case, shall we wrap the session? Lakmal.
Sure, Kalak.
All right. So let me first of all thank you for taking the time and joining with us. As you told us, it's quite early over there. Still, you managed to make it. So let's meet again in the future. In sessions
Yeah,
like this.
thanks, Aklak, and thanks, Kanchana, to allowing me to like giving up this opportunity, and also thanks the community Sri Lanka. So I think you guys are doing a great job. Keep it up. That's good work. Yeah, so I'm very pleased and happy to present this today, my presentation. Yeah, thank you.
All right, quite glad to hear that. So before we actually wrap up, it's pretty much over, but like I told you at the very beginning, we have a little bit of an announcement to make. So let me quickly share my screen and show you what I was talking about. So it's pretty much about this KCD Sri Lanka 2023. So this time we hope to make it as a physical event, and it will be much grandiose than the last year's event. So if you are interested, stay tuned, follow our social media, and let's meet again there quite soon. All right.
Okay, thanks.